Hello, welcome to the third module of the course. This is the first lecture in the module 3 and it is overall the lecture number 22 of the course. In this lecture, we'll briefly discuss about cavity optomechanics. This is going to be an introductory lecture. I will give you a brief overview of what cavity optomechanics is, and as the so-called Fabry-Perot cavity kind of devices or setup are at the backbone of cavity optomechanical system, we are going to discuss in somewhat details about Fabry-Perot cavity because that will help you to appreciate the concepts later. So let us begin. In this lecture, I am going to give you a brief overview of the area of cavity optomechanics. Cavity optomechanics is one of the most useful platforms for quantum technologies. In fact, this platform is useful even in the classical regime. So the question is, what is cavity optomechanics? As the name itself suggests, it is a topic relating interaction between light and mechanics. So suppose this is a mechanical oscillator and they are interacting with each other, and this is mediated by a cavity. That's why it is called cavity optomechanics. So if you have a mirror here and another mirror, but the mirror is attached to a spring, or say the mirror is allowed to vibrate. As you know, you have a so-called Fabry-Perot cavity where both the mirrors are fixed, but here one of the mirror is allowed to vibrate or oscillate. So this is the domain of cavity optomechanics. In fact, the main idea in cavity optomechanics, as put by Marcus Espelmeyer, a pioneer researcher in the area, he says, let me write here, the main idea of cavity optomechanics is to have light interact with a mechanical system in a controlled way via the radiation pressure force. We'll discuss about radiation pressure in somewhat details later on. So this is essentially the idea. Okay, this way one can manipulate light, actually both the state of light and the state of the mechanical system. And since these mechanical systems comes in all shapes and sizes, cavity optomechanics gives us a new way to manipulate light and matter on nano, micro, or even macro scale. And our discussion here will be primarily rely on these review articles. First review article is by Marcus Espelmeyer, Tobias J. Kippenberg, and Florian Marquardt. This is the title of the review article is Cavity Optomechanics. This was published in Review of Modern Physics, and this is a extremely beautiful article. And another article is a short walk through quantum optomechanics by Pierre Meister. It was published in Another Physics. Okay, now so cavity optomechanics is an emerging area in physics and science in general, which utilizes quantum optics tools in condensed matter system. And you know that optomechanics deals how light couples with mechanical system, and in fact there are mechanical systems on micro or nano scale which can vibrate, and typical examples are, say, cantilevers like this, then beams, and all these systems, they vibrate with a frequency in the range kilohertz to gigahertz. Kilohertz means 10 to the power 3 hertz. On the other hand, gigahertz refers to 10 to the power 9 hertz. Okay, and radiation pressure force is the one which is responsible for coupling between light and mechanical motion. In fact, radiation pressure was first predicted by Johannes Kepler in the year 1619, when he observed that the dust tail, as you can see from this plot here, he observed that the dust tail of a comet always points away from the sun. In fact, way back in the early 1960s and 1970s, Vladimir Brzezinski and his co-workers studied radiation pressure effects in the context of gravitational wave interferometers, because at that time people were looking various ways to detect gravitational waves, and Brzezinski and his co-workers came up with many proposals, and eventually, ultimately gravitational wave got detected. And in a way, gravitational wave detectors are, the whole system is a kind of an huge cavity optomechanical system, of course in the very large scale or macro scale. Now today there are variety of optomechanical systems, as is illustrated in this photographs here. Okay, and the mass of the system ranges from gram to zeptogram. Gram to zeptogram. Zeptogram means very small, that is 10 to the power minus 21 gram. And the systems like these are all optomechanical systems. For example, we have these macroscopic mirrors, microscopic mirrors, suspended pillars, trampoline resonator, membranes, microtoroids, double Rix resonators, near field resonators, freestanding waveguide, optical resonators, even the superconducting circuits. Okay, this is also a kind of a it's basically a mechanical oscillator, and it can also be used in optomechanical setup. Then you have these photonic crystals, photonic nanobeam, zipper cavity, cavity nanorods, and cold atom cavities. Interestingly, the mass of the system vary from say gram to very small, say zeptogram, that is on the order of 10 to the power minus 21 gram. So you see that we have this 20 orders of magnitude in terms of mass is there, but the striking and interesting fact is that the same physics is there over this 20 orders of magnitude. And it's very interesting that all these various looking optomechanical devices or system can be modeled by this simple setup, which you have a Febry-perot kind of a cavity with one mirror fixed and the other mirror is movable. Okay, and this model, as we will see its potentiality later on, this model can theoretically explain a lot of the features that is displayed by these various kinds of mechanical or optomechanical devices. Goals of cavity optomechanics. Primarily, cavity optomechanics has two goals. One is to probe fundamental physics, another one is to exploit the optomechanical platform for various technology and applications. In fact, its role in the so-called second quantum revolution is expected to be pretty impactful. Optomechanics can be used to test quantum mechanics in an entirely new domain, that is the domain of macroscopic objects, because so far we know that quantum mechanics is always mainly used to understand lighter objects like atoms, molecules, and so on. In fact, as regards fundamental physics, one pressing issue is to know the boundary between the classical world and the quantum world. Nobody knows exactly when to stop using Newtonian formalism and start using the so-called Schrödinger formalism. In fact, one of the goal is that, or question is that, can we push the boundary higher? That means whether we can use quantum mechanics for higher objects or heavier objects, I mean to say. The trouble is that as we go to larger and larger objects, they couple to the unavoidable fluctuations of noisy environment, resulting in the washing out of quantum fissures. But in principle, yes, we can push the boundary higher, but because of this trouble, as I said, which is actually also known as the issue of decoherence, lot of technological advancement is still to be made to beat this decoherence issue. One example, as we all of us know, is the so-called Schrödinger cat problem, which we briefly discussed about in lecture 1 of this course. Using actually mechanical systems, for example, as shown here in this figure, using a mechanical oscillator, a cantilever, okay, we may create a superposition states of the oscillator at two different locations denoted by K0 and K1. Before making a measurement, we have no idea if the mechanical oscillator is in K0 or in K1. This is equivalent to the Schrödinger cat problem, and it is termed as Schrödinger's mechanical cat. Also, it is known as the Schrödinger's mirror problem. Fortunately, thanks to optomechanics, we are today in a position to create such superposition states, and that may be tested in the laboratory. So that's the reason why understanding quantum mechanics in this new domain is getting a lot of interest nowadays. In fact, it is possible to, and some experiments has already been done to show that it is possible to produce non-classical states of heavy mechanical objects and test quantum mechanics. One of the biggest advantages of mechanical solid state system is its functionality. Say, if we put a conductor on the top of a mechanical system, just like here, it gets coupled to charge. If we put something magnetic on the top, just like here, it gets coupled to spin. Or if we put a mirror, just like here, in the mechanical system, it gets coupled to photons and so on. So the mechanical system acts like a bus system. This way, we have a mechanical transducer that allows us to make different quantum systems interact which otherwise would not have interacted. Maybe we will come to this particular topic later on as well. Now, as regards other applications, and there are many in fact, optomechanical systems may be used for quantum information processing, that is to store quantum information and transfer it. One can couple as an example, a mechanical system, a superconducting qubit to a mechanical system, and then couple it to an optical system to process the information. Now, it is important to note that to study quantum states of such systems, we need to cool these mechanical systems, because they are, why I am saying that, because you know that these mechanical systems are basically harmonic oscillators and they are equally spaced. Say spacing is say h cross omega, and if the thermal energy is greater than h cross omega, then the system will go from the ground state to the excited state, and then actually you will not be able to study the whole thing as a discretized system. These discrete energy levels will not be exploited. So the kbt, this thermal energy, should be much smaller than h cross omega. So as you can see, to have this condition, the temperature should be below than h cross omega by kb. We can just make a rough estimate, and it turns out that because these mechanical oscillators are oscillating in the frequency range of kilohertz to gigahertz, which amounts to temperature far below 20 millikelvin or so. So we need to actually look for some clever methods to cool this mechanical system. In fact, this is going to be one of the topic in this course when we are discussing optomechanics, how to cool a mechanical oscillator to its ground state. And there are other applications. For example, one can have ultra sensitive detection of tiny forces. As you actually you know that if a mechanical oscillator is there, then this Hooke's law, force is equal to say minus kx. From here you can find out the spring constant, that would be say this is the force gradient. Rather than actually tiny forces, we should better say force gradient to be precise. And if we apply force gradient to the mechanical oscillator, it adds some effect to the spring constant of the oscillator, and because the spring constant is associated with the frequency of the oscillator, right, so it shifts the frequency, and this shift is very easy to measure. So that's how we can make ultra sensitive detection of very tiny forces. On the other hand, we can, in the similar way, we can have ultra sensitive detection of masses, because again, if on the oscillator, because say this is the cantilever, if some mass is added to the oscillator, then its spring constant gets changed, and because of that there is a shift in frequency which can further be detected, and this way ultra sensitive detection of masses is also possible. In fact, this is already, for that you need not have to cool the mechanical oscillator to the ground state. This kind of applications are already in place in chemical diagnostic. Okay, and ultra sensitive detection of displacement is also another very important applications. And okay, so what I want to say now is that the primary advantages of optomechanical platforms over that of the others are due to the small size, high quality factor, and because it has high quality factor, so information can be stored for very long amount of time, and its integrability to various other system, as I explained earlier, that we can integrate this system to various other system. And the best thing is that everything can be, as I have put it here, everything can be integrated on a chip, and nano fabrication of these devices are very much possible. Now let us briefly discuss about mechanical effects of light a bit qualitatively. Mechanical effects of light, in particular the so-called radiation pressure force, is at the root of all optomechanical phenomena. In fact, radiation pressure force is behind the most well-known optical tools called optical tweezer, frequently used by biologists. Arthur Eskin of Bell Labs contributed significantly towards understanding of the radiation pressure force, and for which he eventually got the Nobel Prize also. Now, to understand the radiation pressure force, let us consider a typical setup like this. We have a mirror, and on this mirror a photon is getting incident say the photon has momentum h cross k, it is getting incident on the this perfectly reflecting mirror, and as a result of as it is perfectly reflecting, the reflected photon has momentum minus h cross k. So therefore, as you see, that the total change in momentum would be twice h cross k, and thus it is going to experience an overall momentum change given by this particular equation, where okay, let me explain. We have twice h cross k, and which we can write it as twice h cross k is equal to omega by c, and h cross omega is the energy of a photon, so that's why E is the energy of the photon, c is the speed of light. Now if we have an a steady stream of photons, suppose n number of photons are getting incident, then the total force would be we know that the rate of change of momentum is the force, and total momentum would be number of photons into the momentum change due to one photon divided by the time. Okay, this is going to give us the force, and this we can write it as 2p by h, because energy, in fact this I can also write it as from here, this is a total energy, here E this curly E is equal to E into n number of n photons, and then we have twice E divided by C, and then we have also time is also there from here, and energy per unit time is nothing but power, so therefore we can write it in this by this equation also. So the force is equal to twice that of the power divided by speed of light. Okay, this is a useful formula, and we can apply it. For example, the radiation pressure force due to sunlight is nearly on the order of 10 to the power minus 5 Newton, which is a very very tiny force. It's a very tiny force. Okay, let us analyze this radiation pressure force a little bit more, because we'll see this analysis is going to help us in understanding the optomechanical system. So as I already said, that when a photon is getting incident on this mirror, suppose this now mirror is movable, it is a mechanical oscillator, and this is perfectly reflecting mirror, so the momentum change, as I explained, would be twice h cross k, which I can write it as 2s by lambda, because twice, okay, let me do these things here. Let me do the calculations here. Del p is equal to, for when one photon is getting incident, that would be twice s cross k, right? And this I can write it as k is equal to or h cross is equal to h by 2 pi, and k is equal to 2 pi by lambda, so therefore I can simply write it as 2 h by lambda. So this is what is written here. Okay, now this as a result, when the photon is getting incident, the mirror is say getting displaced by an amount delta x, so this much of potential energy is getting stored in the mirror, which is coming due to the kinetic energy of the photon here. So due to energy conservation, I can write this equation, and from this equation we can get this particular equation. Let me explain it again. So what we have here is that the potential energy is half kx square, or which I have half m omega m square, and so delta x square is the delta x square is the displacement of the mirror, and this is equal to the kinetic energy of the photon that is getting incident, delta p square by twice m. So this omega m is the oscillation frequency of the mirror. So from here I can write delta x square is equal to, I have here m square if I take it that side, and I have here del p square, okay, and I also have omega m square. So this will give me the displacement of the mirror. Delta x is equal to del p divided by m omega m, and del p is equal to h by 2h by let me use this formula, 2h by lambda. So this is 2h by lambda m omega m. Okay, now you know that the so-called 0-point fluctuation, which we discussed when we discussed about mechanical harmonic oscillator, though this 0-point fluctuation is h cross divided by twice m omega m square root, or I can write it as x square 0-point fluctuation is equal to h cross divided by twice m omega m, or I can write it as h divided by 4 pi m omega m. So this equation, this one I can utilize it here. So I can write delta x is equal to I can write it as 2 by lambda. This part I can replace by h cross, okay, this one I can replace by 4 pi x 0-point fluctuation square here, or I can write the ratio delta x divided by which the displacement with respect to the 0-point fluctuation, that would be equal to 2 by lambda. In fact, it better I can write it as 8 pi by lambda x 0-point fluctuation. So this is the formula we get when we have this setup. Now if the this mechanical mirror, this movable mirror, has mass 1 nanogram, that means 10 to the power minus 9 gram, this is, or we can consider it as a cantilever also, this cantilever is 10 to the power minus 9 gram as its mass, and the wavelength of the radiation is say 1 micrometer, that is 10 to the power minus 6 meter, then the 0-point fluctuation, the displacement due to the 0-point fluctuation would be on the order of 10 to the power minus 12, and if we put all these things, then you see the ratio would turn out to be only 10 to the power minus 6, which is actually not detectable. What does it mean physically? It means that when a photon is getting incident on a movable mirror, okay, a free photon is incident on a movable mirror, effectively there is no change in the mechanics, there is hardly any displacement that is we can detect. So to have a sizable impact on the displacement of the mirror, or in order to study useful physics, the displacement of the mirror must have to be greater than the 0-point fluctuation, and in order to do that, what we can try by putting another mirror here, and then let us see what happens if we put another mirror there. So this will become basically a cavity. Now when a cavity it becomes a cavity, the photon will oscillate between these two mirrors back and forth depending on the quality factor of the mirror, or the so-called finesse of the mirror. Finesse of the mirror gives the number of round trips of the photon inside the cavity before the photon eventually leaks away from the cavity. So what it happens is addition of the another mirror basically increases the change in momentum del p to uh, f into del p, where f is the, as I said, it is called the finesse of the cavity. Now if the cavity, because the finesse, it depends on the cavity decay time also, the whole thing. So if the cavity lifetime is smaller than the mechanical oscillation period, then it can be shown that this ratio would be given by this particular formula. And it turns out that this displacement of the mirror, the movable mirror, would be greater than the 0 point fluctuation, provided the finesse is greater than or equal to lambda by 2 into twice of the 0 point fluctuation, displacement due to the 0 point fluctuation. So in that case, depending on the cavity, if we put a cavity, then we can always construct such a cavity with appropriate finesse, and then we can have a displacement greater than the 0 point fluctuation, displacement due to 0 point fluctuation, and which is the reason of the popularity of cavity optomechanics, because now we can actually study quantum effects using such kind of a setup. So now the generic model of an optomechanical system is shown here. It is a system with two mirrors, with one fixed and the other movable. Movable mirror is characterized by mass m, oscillation period omega m, and a phonon decay rate gamma m. As you know, quanta of this mirror is movable, that means it is vibrating, and the quanta of vibration is called phonon. The cavity is characterized by the cavity resonance frequency, say omega c, and it's a cavity decay rate kappa or k. On the other hand, the incident laser light is characterized by its wavelength lambda, its frequency omega L, and the power P. The purpose of the cavity is to boost the light field effects, and one of the mirror is fully reflecting, this one say, and while the other one is partially reflecting, so that light can enter into the cavity. Now there is a basically certain condition has to be satisfied for that light can enter into the cavity, and that to understand that, we need to revisit the Febry-perot cavity. As you can see from this diagram, that the system is primarily a kind of a Febry-perot cavity, and it may be now useful to digress a bit and discuss about Febry-perot cavity in some details. So let us discuss Febry-perot cavity now. We'll start with the simplest case of a planar cavity of length, say L. So planar cavity means we have two plane mirrors separated by a length L, and let us assume that these two mirrors are perfect reflectors. And in order for a plane wave to exist in the cavity, it must return exactly the same phase after one round trip through the cavity. Okay, so that has to be the condition, and in this case it will constructively interfere with itself. Otherwise the phase will precede on each successive round trip, and eventually it is going to lead to destructive interference. So the round trip accumulated phase must be some integral multiple of 2 pi. Now because in one round trip the total length covered would be 2L, and therefore the phase would be 2L into k. K is the wave vector, and that has to be integral multiple of 2 pi. So m is an integer, say m is equal to 0, 1, 2, so it is an integer. And this is the condition. This is called the cavity resonance condition. This is called cavity resonance condition. In fact, because you know that k, the wave vector, is associated with the angular frequency of the wave omega by this relation, k is equal to omega by c. Again, you know that omega is equal to 2 pi c by lambda, wavelength of the radiation. So using this, we can write various resonance conditions. For example, cavity allowed wave number from this relation would be, say, km is equal to, it would be, as you can see, this would be simply pi by L into m. Okay, and then using either omega or lambda, we can have cavity allowed wavelengths as, say, lambda m is equal to 2L divided by m, and frequency, in terms of frequency also we can write, because you know that omega is related to frequency 2 pi, as omega is equal to 2 pi nu. So therefore nu m, this is the allowed frequency, that would be m into c divided by 2L. Or we can also write it as omega m is equal to m into pi c by L. So these are the same conditions written in different form, and all these forms are useful depending on the situations. Either of these forms can be used, and we'll use that. Now the corresponding spectrum, if I plot intensity inside the cavity versus the frequency, then only those frequencies or wavelengths would be allowed to enter into the cavity which is going to satisfy the resonance condition. So therefore, for example, if it satisfies this conditions in nu m, then you will have a sharp peak inside the cavity. Or if it satisfies, say, your m is equal to nu m plus 1, then also you will have a peak. Otherwise, in between here will not have any radiation, because the resonance condition is not going to be satisfied there. And here it would be, say, we'll have this would be nu m minus 1, and so on. You will get a lot of peaks in between. Now there's a very important quantity, the frequency spacing between these peaks. This is a very important quantity. This frequency spacing is called free spectral range. Free spectral range, or also called FSR. This quantity is of immense significance, and this is simply the frequency spacing. So therefore nu m plus 1 minus a nu m. If you from this relation, you can easily see that this would be simply c divided by 2L. Okay, and this is an important quantity, and it is worth remembering, FSR. Now you know the real cavities involve some loss of light on each round trip, and this loss actually damp the amplitude of the cavity. So let us consider again this cavity. If let us say, suppose light is circulating inside the cavity, and after some round trip, suppose its electric field amplitude is, say, En, and reflectivity of, say, this mirror is R. Let us say both the mirrors has the same reflectivity for simplicity purposes. Then the amplitude of the wave is going to reduce by a factor of R on each round trip. So after n plus 1th round trip, its amplitude would be reduced by a factor of r, okay, like this, the amplitude will reduce. R is less than 1. So so we are just writing about the amplitude here. So this is what is going to happen. Okay, now here En is basically the electric field amplitude of the plane wave on the nth round trip, as I said, through the cavity, and the loss due to R could be some transmission of the mirrors, okay, or losses around the edges of the finite size of the mirror, scattering from some, suppose some gas is there inside the cavity or objects inside the cavity, and so on. On one round trip, the phase of the plane wave is going to change, and it is going to change by, say, phi, delta phi, and of course the phase would be one round trip. As we know, this would be 2k into L, and which I also can write it as 4 pi. K is equal to 2 pi by lambda, so it would be 4 pi by lambda into L, and therefore the electric field after n plus 1th round trip, it would be, now here I have written the magnitude. So if I take phase also into account, then it would be R, you will have e to the power, phase is I 2kl, okay, and this would be En. So this is what is going to we are going to get. Now let us assume that this R, this quantity, is real, and then the total wave, if I consider all the round trips, the total electric field, say initially we had electric field is E0, then after one round trip we have E1, and then E2, E3, and so on, and this is related to this quantity by dint of this relation. So immediately you can see that I can write it as E0 1 plus E1 would be E0 e to, R e to the power I2kl, then the second one, so you can easily make it out. This would be R e to the power I2kl whole square, and so on. So you will get a geometric series, and this is very simple to work out, and you will get this relation, that would be E0 divided by 1 minus R e to the power twice IKL. So using this relation, now I can easily get the intensity inside the cavity. Just to remind you that intensity is related to the electric field by this expression. If I consider that the inside the cavity the refractive index is 1, then it would be intensity is half epsilon 0 c E square. Okay, so this we know. So utilizing this relation, I can write the intensity inside the resonator would be equal to, if you take the mod square, you can easily get this expression. It would be I0 divided by 1 minus R whole square plus 4R sine square KL. So this relation can be worked out very easily. So this is the intensity we are going to obtain inside the cavity. A typical intensity versus frequency for a Fabry-Perot cavity would look like this. Let us say we have in the y-axis this intensity and the x-axis frequency. Let me plot it. Let's say this is I maximum. I will explain these terms a little bit later, and this is a I minimum. Intensity will oscillate between minimum and maximum, and it will be like this. We'll have several peaks like this. Okay, and so on. And this peak should be there provided the resonance condition is getting satisfied. For example, when the frequency is integral multiple of c by 2l. In fact, c by 2l already you know this is nothing but the free spectral range FSR. So rather let me write it up m into FSR, and this would be m plus 1 into FSR, and you know the distance between these two is basically free spectral range, and this would be m minus 1 FSR and so on. We'll get lot of peaks like this, and all this resonance peak would have width, that is this width is the full width half maximum. It will have full width half maximum, and we'll show that this full width at half maximum, or this resonance width is would be actually, it's a ratio between the free spectral range and the finesse of the cavity. So finesse of the cavity is a very important quantity, and this is defined as the ratio between free spectral range divided by the bandwidth. In fact, this bandwidth is nothing but the full width at half maximum, delta nu FWHM, and free spectral range, let me denote it by delta nu. Now, from the expression that we obtained a little while back, that is I is equal to I0 divided by 1 minus R square plus 4R sine square KL. From this we can work out the maximum intensity and the minimum intensity. Maximum intensity we'll get at resonance. At resonance, this sine KL would tend to 0, because at resonance, as you know the resonance condition, this would be KL is equal to integral multiple of pi, so therefore this term will vanish. So you will have the maximum intensity, that is I max is equal to I0 divided by 1 minus R whole square. On the other hand, far off resonance will have sine KL will tend to 1, so therefore we'll have, as you can see from here, when it will become maximum, we'll get minimum intensity, that is I minimum would be equal to I0. If it becomes equal to 1, then you immediately see that this will be I0 divided by 1 plus R whole square. Okay, now let us calculate the FWHM or width of the resonance delta nu. Let me do the calculation of delta nu full width at half maximum. This is pretty easy, because you know that at full width at half maximum, let us say k is taking the value k plus minus, then the intensity, because it is maximum, half maximum, so you have half I max, right? That's the half of the maximum. So if I now put the expression of I from here, this one, and for k is equal to k plus minus, then I have I0 divided by 1 minus R whole square plus 4R sine square k plus minus L, and that would be equal to half I0 1 minus r whole square. From here you can immediately get sine square k plus minus l is equal to 1 minus r whole square divided by 4r. Now okay, now you see you have omega angular frequency plus minus, I can write it as c into k plus minus. So therefore I have from here sine square omega plus minus, in fact here, okay, L into omega plus minus by c, this is equal to 1 minus r whole square divided by 4r. And from here you can get omega plus minus is equal to, with some factor is there, but okay, this is what you will get. It would be c by l sine inverse 1 minus r divided by 2 into square root of r. Now under small angle approximation, because this r reflectivity is usually 96 to 99%, 98%, so for sine function we can make the small angle approximation. So under small angle approximation we can write omega plus minus, that would be nearly equal to plus minus c by l, and we'll just keep this term 1 minus r 2 into square root of r. Okay, now if I define this full width at half maximum, that is basically delta nu fw hm, that is omega plus minus omega minus, okay, divided by 2 pi. And if you work it out from here, you will get it as c by 2l 1 minus r pi into root r, and c by 2l is nothing but the full free spectral range, that is we are denoting it by delta nu, and this is 1 minus r pi into root r. And we know that the finesse is delta nu free spectral range divided by the full width at half maximum. So from here we immediately get an expression for the finesse for this planar cavity when both the mirrors have reflectivity r. Okay, so this is a important quantity. Now in terms of finesse, we can rewrite the intensity expression, that is the expression that we had earlier was, I'm repeating it again, I is equal to I0 1 minus r whole square plus 4r sine square kl. This we can rewrite in the standard form, and that would be I is equal to I max, you can please verify, it would be 1 plus twice into finesse by pi whole square sine square kl. So this is the standard form for expression for the intensity of a Fabry-Perot cavity. Now let us discuss about photon lifetime inside the cavity. Photon lifetime inside the cavity. You know that losses in cavity can come from a number of sources. The mirrors can lead to intensity loss due to partial transmission and absorption of light in the reflective coating. There are coatings are there, so because of that also light can be lost or photon can get lost. Then scattering due to the surface roughness, and so on. Let us say PS is the survival probability of a photon. PS is the survival, okay, let's say PS is the survival probability of a photon inside the cavity after one round trip. Okay, actually, if both the mirrors has reflectance or reflectivity R, then PS is equal to R square. Otherwise, if one mirror has reflectivity say R1, the other one has R2, then PS would be equal to R1 into R2. Anyway, we are assuming that both the mirrors are having the same reflectivity. Now, in terms of using this expression, we can rewrite the expression for Finesse in terms of this survival probability, because we have this expression for the Finesse. So Finesse in terms of survival probability would be pi into PS to the power 1 by 4 divided by 1 minus square root of PS. So the probability, this is we are going to use now, the probability that a photon get lost, the photon get lost with probability, actually rather let me write it as the probability that the photon get lost after one round trip. So it is clearly 1 minus PS, because PS is the survival probability of the photon after one round trip. So on the average, what would be the number of round trips would be round trips on the average, rather let me write number of round trips on the average for the photon would be 1 divided by 1 minus PS. Okay, now the round trip time is easy to calculate, because we know that the cavity has length 2L, so the photon has to cover a distance of 2L, and speed of the photon inside the cavity is c, let us say, then round trip time would be 2L by c, which we can actually, rather than t, let me write is tau tr. And in terms of free spectral range, we can write it simply as 1 divided by free spectral range, because c by 2L is the free spectral range. So this is an important quantity. This is the round trip time of the photon. So lifetime of the photon inside the cavity, let me denote the lifetime of the photon as tau p. This is the lifetime of photon inside the cavity. So that is clearly, it should be equal to the round trip time into the average number of round trips inside the cavity. So using the expression that we derived here, that would be photon lifetime we'll have as 1 divided by free spectral range into 1 minus PS. Okay, now actually for a good resonator, or good cavity, for good cavity, this survival probability is nearly 1. So therefore we can nearly assume that square root of PS is equal to 1, or we can write PS to the power 1 by 4 to be nearly, you can set it as 1, and we can write 1 minus PS is equal to 1 minus square root of PS into 1 plus square root of PS. This I can write because of this approximation, I can write it as 2 into okay, from here I'll get 2 into 1 minus square root of PS. So using this I can write down the expression for the finesse. I can simplify it as for a good resonator or a good cavity, it will be pi divided by 1 minus square root of PS. And ultimately what I can do, I can express the photon lifetime in terms of finesse as this, that would be 1 divided by 2 into free spectral range, and this would be 1 minus square root of PS, and this I can further write as finesse divided by 2 pi into free spectral range. So because I already know that free spectral range and finesse is associated with the full width at half maximum, so therefore I can write it as 1 by 2 pi, and this is nothing but full width at half maximum, delta nu full width at half maximum. Or I get a very interesting relation, that is photon lifetime into the width of the resonance peak, that is delta nu at full width, delta nu full width half maximum is equal to 1 by 2 pi, and this is known as cavity uncertainty relation. Cavity uncertainty relation. Let me stop here for today. In this lecture, after giving a brief introduction to cavity optomechanical systems, we discussed about Fabry-Perot cavity. In the next lecture, after completing our discussion on Fabry-Perot cavity, we'll see how to guess the optomechanical Hamiltonian, and also we'll try to understand the basic physics based on this Hamiltonian. So see you in the next class. Thank you.